So in our last video we defined what it meant to be an absolute max or min or a relative max or min. We talked about what the extreme value theorem said, and then we looked at the idea of critical points where the derivative equals 0 really shows us potential high or low points. And so we're going to take that one step further in this video. So how do we actually go about finding these absolute or relative extrema? I'm just going to give you a four-step process here. First of all, find those critical points. So find f prime, set it equal to 0, or figure out where f prime is undefined. Once you have those potential x values, you're going to plug them into the function and figure out the y values that go with them. And then also don't forget to do the endpoints. And then you compare all of that data and figure out where the highest of the highs and the lowest of the lows are. Let me give you a little picture to demonstrate. So in this picture, if I were to take the derivative of whatever function I have here, I would find that that derivative would equal 0 at this x value, and that 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 x value. And then I would also be looking at the x values that gave me the endpoints there. And so if I were to take 1, 2, 3, 4, 5, 6, 7, 8, those 8 x values, plug them into the original function, almost make a t-chart, make an xy chart, and then in the end I compare those final y values. Those y values will show me that it's the highest of the highs right there and the lowest of the lows right there, and that's going to be our strategy in the next two examples. So this part right here just says, remember that the critical numbers, those critical points are x values, the max and mins are y values, and so just make sure that we define things the right way, that we're clearly writing out what we intend to, and so this gives you a good way of describing that. Okay, so how do we find the extrema for the function 3x to the fourth minus 4x cubed on the interval from -1 to 2? So first of all, I would challenge you maybe to graph this and just see what it looks like. If we just go through the algebra though, I notice that it's a polynomial, so it's going to be a nice continuous function. It is on a closed interval. Those two things tell me that the extreme value theorem should work. It means that I do have an absolute max and min. So the first thing I do is I find the derivative, and then I just know that later on it's going to be nice to kind of have that derivative factored apart. So these two things have 12x squared in common. I take that out to the front. And then I want to know, when will the derivative equal 0? So I say derivative equals 0. So now 0 is going to equal this thing, and this will be a true statement either at x equals 0 or x equals 1. And then I also want to ask myself when the derivative would be undefined. Well, this thing right here is never undefined. I'm never going to end up dividing by 0. There's never values that I couldn't plug into that, so that's a dead end here. And then I go and I make my t-chart. And so I have endpoints of -1 and 2, and I found the x values of 0 and 1 are my critical points. I take these 4 x values, I plug them into the function up there. Do that on your calculator if you need to. And I get those y values. And so that tells me that at x equals 2, 16 is my max, and at +1, I get to the lowest part of a y value of -1, so that's my absolute min. And beyond that, not too complicated. The only thing is, I mean, really from this point on, it's all just kind of review of pre-calculus, you could say. It's this part that we're adding. Okay, last example, we are looking at 2x minus 3x to the 2/3 power, it looks like. And again, we have a closed interval. You might need to do a little bit to show that it is a nice continuous function on this interval, but on this interval it would be just fine. So we take our derivative. So I'm using the power rule throughout here, and then I just rewrote it so that this was not in power form, but more in a fraction form, a root form. And then think about when that derivative is going to be undefined. Well, I'm going to be dividing by 0 if I plug a 0 in, so that's where this is coming from. I set the derivative equal to 0, so derivative, now you're equal to 0, and I'm going to work backwards to solve. So let's see, what did I do here? You could think of me adding this whole chunk to that side. So this whole thing came over to the other side, and now it's going to be positive. And I could really that might make that a little bit easier to read. I brought the cube root of x that was in the denominator, I multiplied by that and brought it to both sides, so now I have 2 times the cube root of x on the left side, a 2 right there. What's going to make that true? That statement would have to be x equals 1. I could do a little bit more algebra if I had to, but x equals 1 is going to be where the derivative equals 0. So from there, I go and make my t-chart. I have a -1 and a 3 for my endpoints. These are the critical points that I came up with. I plug them into the original function and I get those values. And from there, the highest value I get is a 0, so my absolute max is at 0. The lowest of the lows is at -5, so my absolute min is right there. And that's generally, for now, all that we do when we find the absolute maxes or mins. We test the few points that we know are potential spots and we just compare them.